expense of Mr. Robert Wexler. It's really exciting to reflect on the time that Rob has spent here at the University of Pennsylvania. As you all know, the PhD is mostly a research degree. So Rob pursued advanced coursework and then conducted independent research studies in theoretical physical chemistry, looking at two-dimensional materials and then moving on to heterogeneous surface catalysis, materials design, and developing new theory and algorithms for enabling greater study in these areas. Rob has also been the pioneer of embracing modern computational tools and methods in my group, and so many other people who are with us today have benefited from the exchange of ideas from different communities that Rob has orchestrated, and that has been exciting to see. Many people often think of the distinction between student and teacher as a large one, but in this case, I think that everyone around Rob, including me, has learned as much from him as we have been able to teach him. And so Rob has achieved at the highest levels in his research, and he will tell you about some of his findings this afternoon. A title that encompasses much of his work, but actually not all of it, is Toward Realistic Modeling of Catalytic Surfaces from First Principles to Machine Learning. Rob, we welcome you to deliver your PhD thesis.
Okay, can you hear me okay? Is it projected? Okay, great. Thank you so much, Andrew, for the introduction, and I want to thank everyone for being here today to see a presentation of my work for my PhD. It really means a lot. So without further ado, let's go. And as Andrew said, today I'm going to be looking at some studies and some new methodology that we've developed in the RAP group to more realistically model surfaces for catalysis. And we use techniques from first principles quantum mechanics all the way to machine learning. So as an outline for my talk, in the first part, I'm going to discuss electrocatalytic hydrogen evolution on nickel phosphide materials. And I'm going to show how you can use first principles density functional theory calculations to elucidate a number of the catalytic properties of the system. And then also use machine learning then to go back and learn the quantum mechanical information to design new material systems. And then in the second part, I'm going to show you a new methodology that we've developed to better enable prediction of surface phases that are catalytically active and to enable the computational catalysis community to more realistically model surfaces that are catalytic. So again, the first part I will talk about, first, the effect of surface reconstruction on the hydrogen evolving activity of nickel phosphides. So before that, I'll motivate why we might be interested in hydrogen, and specifically the hydrogen evolution reaction. And the reason is that hydrogen has many important uses. It can be used as a clean fuel or in energy storage. It's very important in the Haber-Bosch process to generate ammonia for fertilization. It's used in plastics and pharmaceuticals, in hydrogenating oils, and it's also used in cleaning and hydrodesulfurization of fuels, such as petrochemicals, also natural gas. So as you can see, hydrogen is very important industrially. However, the current industrial techniques for its production are not ideal. They're not ideal in the sense that it's a two-step reaction to form hydrogen. The first step is steam-methane reforming, where we react methane with steam to form hydrogen and carbon monoxide. But then we have carbon monoxide, so we want to remediate that. So we react that with water, and we form more hydrogen and carbon dioxide. But as you can see, there are three problems with this. First, it takes in fossil fuels, so this is a natural resource that we're running out of. Second, this process is endothermic, so we're pushing against thermodynamics to make it occur. And finally, we generate greenhouse gases in the end, and this is obviously something that we are very alert about these days and trying to alleviate. One alternative to the current industrial techniques for hydrogen production are electrochemical hydrogen production from water. So this involves electrolysis. We apply voltage and split water into oxygen and hydrogen. There's one material called a cathode, which does the reduction, which takes water and converts it to hydrogen. And specifically, it takes protons in solution and electrons in the cathode itself to generate hydrogen gas. So you can see here, this is the red electrode set up here in our 3-electrode setup. So we apply a voltage on this working electrode, and this causes the protons to be reduced into hydrogen gas. There also has to be a counter electrode which balances the charge. So here we've lost 4 protons, so we need to regain 4 protons. That occurs here at the counter electrode, and this is also called an anode. And this does the oxygen evolution reaction, which takes 2 water molecules and generates 4 protons and electrons and an oxygen gas. And so these are 2 of the electrodes we need. The final is a reference electrode, and this is going to be connected to our working electrode in order to measure against some solid reference what is the potential that we're applying. So this all looks great. We can split water into a fuel hydrogen that we need. However, the best catalysts for doing this reaction are far too expensive. And that can be seen here on this plot, which is called a volcano plot. On the y-axis is the rate of the hydrogen evolution reaction. So here is very slow rate, and here is very fast. And on this x-axis, we have the binding energy of hydrogen. So this will be very strong binding, and this will be very weak binding. There are 2 main trends that you can see here. This first trend, this blue line, shows the rate of binding hydrogen to the surface. So you start with a proton, electron is on the surface, and you bind hydrogen at the surface. And you can see that the rate decreases as the binding strength becomes weaker. And that's because the interaction between hydrogen and the surface is weaker, and so therefore it's not going to stick strongly to the surface, and its rate will be slow. So down here, where the rate is very small and the binding energy is large, this is a bare surface. On the other hand, we have this red line which corresponds to the rate of unbinding hydrogen. So we start with a hydrogen on the surface, it reacts with a proton and electron, and it forms a hydrogen gas molecule. And so as you can see, that when binding is very strong, so you have a hydrogen poison surface. And hydrogen is bound so strong that it doesn't want to detach to form a hydrogen molecule. However, as you weaken the binding, this rate increases because hydrogen doesn't mind leaving the surface. So obviously, the rate of binding and unbinding have to work together, and so you get an observed rate shown here by the dashed green line. And at the very top of this dashed green line, which happens to correspond with a delta G equals 0, this is what we call a thermoneutral condition, we have platinum. And this has the highest rate, but obviously, as we know, platinum is really expensive. So an alternative would be to use something like nickel, which is cheaper, but this offers a much lower rate because it binds hydrogen too strongly. Something that was discovered about 10 years ago was that you could alloy nickel with phosphorus, and this could push you towards the correct part of this volcano that is the observed rate. And this is something that I'm going to explore a bit more today using first principles of machine learning. So a little primer on the materials that I'll be talking about today. The first, they are nickel 2P and nickel 5P4. So these are 2 different nickel phosphides with different compositions in their bulk. And they both they both have a hexagonal crystal structure. And so you can see the crystal structure right here for nickel 2P. You see that this dash line is the unit cell. And so this repeats in all directions. And you have 2 layers, a nickel 3P2 layer, a nickel 3P layer. And in this layer, we have a square pyramidal coordination with phosphorus. You can see that right here. And we also have a nickel 3P2 layer, where you can see the coordination is different. It's a tetrahedral coordination in this layer. For nickel 5P4, it's a much larger unit cell, meaning that there's less symmetry in the crystal. It's a little bit more complicated. And there are 3 main layers. There's a nickel 3P3 layer, where you have a square pyramidal coordination with phosphorus. A nickel 3P2 layer, where you have a seesaw coordination with phosphorus. And a nickel 4P3 layer, where you have a trigonal pyramidal coordination with phosphorus. So as you can see, these materials have many nickel sites with different coordination with phosphorus, and so therefore there could be many possible active sites that we need to investigate. And just as a benchmark, you can see here are some experimental measurements of the electrocatalytic performance of these nickel phosphides in splitting water to form hydrogen gas in 1 molar sulfuric acid. So here you can see the compound, and these are the voltages, the reducing potentials needed to apply versus the RHE to generate either -10 or -100 milliamps per centimeter squared. And so what you can see is that nickel 2P requires -42 millivolts, and for 10 milliamps per centimeter squared, and for 100 it needs -100 millivolts. And the key thing you can see here is that this number should decrease. If this reducing potential becomes smaller, that means you have to apply less energy in order to generate hydrogen gas. And so platinum, which is our best material, the state-of-the-art material, you can see that this nickel 5P4 material performs just as well. So this is really exciting because nickel 5P4 is made from abundant materials. Nickel 2P, on the other hand, is a little bit higher, but still very good compared to other electrocatalysts to date. Okay. So the goals of my talk today will be to, more generally, to understand and develop more inexpensive catalysts for the hydrogen evolution reaction, and specifically we'll apply a paradigm towards studying the catalytic activity of nickel phosphides that is as follows. First, we'll elucidate what the surfaces of Ni2P and Ni5P4 are, because the surface is the key place where the chemistry will happen, and so we need to have an accurate model of the surface. Then we will develop a picture of what the surface phase diagram looks like in aqueous solution. So this is very important because we're dealing with electrocatalysts. Then we'll move on to model the hydrogen evolution reaction on these surfaces that we find to be stable under specific conditions. And then finally, using this knowledge and combining our results with some machine learning techniques, we can elucidate new features for designing new catalysts. Okay, but to start, and I'll do this very briefly, I'll talk about the methodology that we use in order to calculate these properties. And the method we use is called density functional theory. It was originally, this idea of a density functional theory was originally proposed in 1964. And the general idea of density functional theory is that total energy can be written as a function of the electron density. And this differs from wave function-based methods where you need to know the many-body wave function. And the great thing about knowing the energy as a function of the density is that the density is a real and experimentally measurable function. And so this is something that experimentalists can measure, and therefore there's a very strong physical intuition for it. The equation for the energy as a functional of the density is shown here. I'll break it down like this. The first term is a classical electrostatic interaction between the nuclei and electrons. This second term here is a classical electrostatic repulsion between the electrons. This term here, this is the first real quantum mechanical term. This is the kinetic energy of the electrons, and you can see that we've had to replace the density with a wave function. This is something that we do, and these are called Cohen-Sham wave functions. And then this last part right here is everything quantum mechanical that we haven't captured up to that point with these three terms. And so this includes electron exchange and correlation effects. And we have found very good approximations for this particular term in the energy functional that we have applied in this research today. And finally, from this energy, which we can calculate from the following terms, we can then calculate the differences in energies between different steps in electrocatalytic reactions, and therefore calculate delta G's, which are of major interest to us. All right, so now that I've given you a bit of background about nickel phosphides and hydrogen evolution catalysis, I'll describe first how the surfaces of nickel phosphides are enriched with phosphorus and how this could potentially play a role on their catalytic activity. So this work was published in Chemistry of Materials. So the first point that I would like to make is that it is often the case that the surface of a material looks different than its bulk. And this is a property called surface reconstruction. And so here are two classic examples of surface reconstruction. We have silicon 111 7x7. And as you can see here, we know that silicon has a particular bulk structure, but as you can see, there's a very diverse coordination environment of silicon on the surface with varying pores of varying size. And if you look from the side, you can actually see here's a regular terminated silicon surface, and then it forms an add layer with add atoms, dimers, rest atoms, and angle cavities. And so this is just a single element material that can undergo a very dramatic reconstruction, which can affect chemistry on that surface. Another example is that of silver 110. And what we find through scanning tunneling microscopy measurements is that actually the surface prefers to have missing rows, and so it has this jagged structure. And so from this you can see that surface reconstruction is something that occurs, and these are just two of many examples. So for the nickel phosphides, it's actually interesting because not many people have studied the reconstruction behavior of phosphide materials. Mostly it's been done for single element materials and also oxides. But we're the first to really look into the phosphide surface reconstructions. And so here I'm showing you again the side view of first nickel 2P. And we look specifically at this nickel 3P2 layer, which we find to be more stable than the nickel 3P. And then we look at how different events can occur at the surface that stabilize it. And so the top view of the surface is shown here with the red being the unit cell of the surface. And then on that surface we have two distinct sites that are interesting. First we have this site right here, which has 3 nickel atoms forming a triangle, which I'll refer to as a nickel hollow. And at the nickel hollow, it isn't just a flat surface, it actually likes to bind a phosphorus atom. And then additionally, there's also a nickel 3P subunit, which instead of having an add atom, it actually sits in the plane of the atoms. And so this is really interesting because this means that phosphorus is enriching the surface, and that's going to block these nickel 3 sites from doing chemistry. For the nickel 5P4 material, it's a little bit more complicated. Again, I showed you the bulk crystal structure was also more complicated. But the key features are as follows. So again, we have one of these nickel 3 holocytes, and a phosphorus atom binds at the top, so that again caps this site. But in addition to a nickel hollow, we have a phosphorus hollow. And that phosphorus hollow is shown here, with the 3 phosphorus forming a triangle and a phosphorus on top. You can see it right there. And so again, this is capping this phosphorus hollow, preventing it from doing chemistry at the hollow site. And also, this is really unique because phosphorus forms a tetragonal bulk material. And so what you see here is actually something similar to bulk nucleation of phosphorus on the surface. And then finally, at this nickel 6P5 subunit right here, shaded in yellow, you can see that a phosphorus binds, and it actually interacts with the nickel 3 phosphorus atom, forming a P2 unit. And it's also well known that phosphorus can form a stable dimer. And so we see nucleation of phosphorus phases on the surface, which is a very new thing, and hasn't been observed for oxide systems because oxides can't form stable connected chains of oxygen, whereas phosphorus and its neighbors on the periodic table, sulfur, they can form extended chains in their elemental form. And so that makes their surface reconstruction behavior very interesting. Okay, so now that we've painted a picture of the surface reconstruction of nickel 2P and nickel 5P4, I go on to study how these reconstructions change in aqueous solution. And specifically, I find that there's an active role of phosphorus in catalyzing the hydrogen evolution reaction. So first we take a look at the nickel 2P surface that I showed you before, and I'll focus in on that nickel hollow site that I was describing. So if you apply 0 volts versus the standard hydrogen electrode, what you find is that hydrogen binds very strongly at this nickel hollow site, and the phosphorus atom that I showed you on the previous slides doesn't exist there, because the binding of hydrogen is stronger. However, as you reduce the system, once you get to minus 0.21 volts, what you find is that phosphorus comes back to the surface. However, in an aqueous solution, it doesn't come back as phosphorus, but rather it comes back as these pH2 or pH3 adsorbates on the surface. And these are actually rather interesting, which I'll show in a second. But these hydrogens are bound almost perfectly when it comes to doing the hydrogen evolution reaction. If you reduce the system too far, these phosphoruses like to desorb into solution as an aqueous phosphine under low concentrations. And what is preferred is that hydrogen will bind a bridging site with nickel, and there will be a hydrogen molecule physisorb to the surface. And so for nickel 2P, it's clear that if hydrogen is bound too strongly at this nickel hollow site, then the activity must come from this adsorbed phosphine intermediate. And what we find is that this is actually the case, that this pH3 is the active site, and then it binds hydrogen with a 0.14 EV delta G. And this is much closer to the top of that volcano I showed you previously, and I'll show you in a second. For nickel 5P4, unlike the case that I showed you previously, which was for solid-state synthesis environments, in an aqueous solution, it doesn't form phosphorus enrichment. However, it is still the case that phosphorus is the key to the chemistry. And so you can see here that the nickel hollows bind hydrogen strongly, and then these phosphorus hollows each of the phosphorus can bind 1 hydrogen. And this P3 site becomes the active site, and its binding energy is even closer to 0, which is what we want. And as you can see, it's the absolute value is closer to 0 than for nickel 2P, which means that it should be more active. And the reason why this binding energy is weaker at these sites is because as hydrogens start to bind at each one, so one here, one there, one there, they start to repel each other. An electrostatic repulsion. And this repulsion causes the binding energy to decrease until the saturation point is reached. And so from here you can see that when here's the plot I showed originally on a while ago, that as you start from nickel, which binds too strongly, if you alloy with phosphorus to get nickel 2P, then you will get binding energies up here on the volcano. So you've gone closer to the top, which means your activity is increased. Then for nickel 5P4, you're even closer to the top and getting closer to platinum. And so this can explain why nickel 2P is not as good as nickel 5P4, which is almost as good as platinum. It's because of where they fall in this volcano plot. And to look a little bit more deeply into how hydrogen interacts with the phosphorus hollow, I've plotted the binding energy as a function of the concentration of hydrogen on the surface. So what you can see is that the first 3 hydrogen, right here, bind very strongly at nickel hollow sites. The next 9 hydrogen bind at these P3 sites, because each of them can bind 3 hydrogen. And as you can see, that as you increase the coverage, the binding energy weakens. And so this can be seen here on this volcano plot rendering, where you start from nickel. Here's the first phosphorus hollow site that fills. But once you get to the saturation point, you can see that the binding energy is weakened to the point where now it's almost at the top of the volcano. And so this is an ensemble effect that's contributing to the activity of the nickel 5P4 surface. Okay, so now that we understand what are the stable reconstructions of the surface in aqueous solution, and we've mapped that to where they fall on the volcano when it comes to the hydrogen evolving activity, we want to try to find a way to increase the activity of nickel 2P. And we found a way by doping with nonmetals, and found that these apply chemical pressure. And I'll describe that now. And we use both first principles and machine learning to elucidate this effect. So this was published last year in JACS. So here I'm showing you again, you've seen this before a few times now. This is the unreconstructed nickel 2P surface. And again, we see here's the nickel hollow site. And as I told you before, at 0 volts versus SHE, this binds hydrogen far too strong. And so therefore it's an inactive site towards hydrogen evolution. Surrounding it, however, are a number of phosphorus sites. And because the nonmetal can play such a role in the catalytic activity of the material, we thought it might be interesting to look at how substituting phosphorus with other nonmetals might affect the catalytic activity. And so we did this. And you can see here these phosphoruses are numbered. And this numbering corresponds to the order in which we substituted the phosphorus with another nonmetal. And so, for example, if we substituted 4 of them with sulfur, for example, then sulfur would go at 1, 2, 3, and 4. So here you can see the results of these calculations. The binding energy shown right here. Our dotted line here is what we're trying to achieve. And this point right here is what we start with. And this is the concentration of the dopant of different nonmetals. And here are the different species that we considered. Okay? The first trend that you can see is for arsenic and silicon. And no matter what the concentration you dope around the active site, they don't affect the catalytic activity. For the 2P nonmetals, what happens is that as you dope around the active site, you start to weaken binding significantly. In fact, you achieve some binding states that are very close to this thermoneutral line. However, as you increase the concentration beyond that of around 2 or 3, you see that the binding becomes more disordered because the nickel site is changing dramatically, its geometry is changing, but also the binding becomes too weak. An alternative case is that of doping with chalcogens like sulfur, selenium, and tellurium. And what we find is that at low concentrations, they actually serve to weaken the binding, which is something that we want compared to the bare nickel 2P surface. But that at too high of a concentration, they start to strengthen binding again. And so from this, we learned that both 2P nonmetals and chalcogens can activate the nickel hollow site by bringing us closer to this dotted line. But binding near 0 isn't the only prerequisite for being a good catalyst. You also have to be stable. And so substitution has to be thermodynamically spontaneous. So here you have the free energy of substitution as a function of concentration of the dopant again. And above this are going to be unfavorable substitutions. So for example, silicon, boron, carbon, and nitrogen, they're all unfavorable, so you can't actually dope with these materials. So unfortunately, those 2P nonmetals, which can give you exactly thermoneutral binding, can't actually be accessed thermodynamically. There are, however, some that can, including arsenic, sulfur, selenium, and tellurium. And as I showed you before, arsenic isn't interesting because it doesn't really change the binding energy. But sulfur, selenium, and tellurium do. And so under moderate doping concentrations, we can both dope the surface thermodynamically, it's thermodynamically favorable, and also it will weaken the binding in the way that we want. And so only the heavier chalcogens will both activate the nickel 3 site and also replace phosphorus. And so once we were able to determine this as a candidate's material class for doping, we wanted to understand how did the dopant really affect the binding energy. And to do that, we calculated a number of structural features of the systems like bond lengths, bond angles, but also electronic features like the charges on the atoms, and tried to map that to the binding energy to come up with some model that could help us understand the trend that we were seeing. And so to do this, we used a decision tree algorithm, and that's what I'll explain now. So you can imagine that you have a data set, one that has m rows and n columns, so m rows going down and m columns wide, and where the x values in this data set correspond to our chemical features, like bond length or the charge on an atom, whereas y is our chemical property. That's the binding energy in this case. So what we do is we take this data and we dump it into a bucket, and this bucket is right here. And then on that bucket, we ask it a question. And we ask a question based on xi, which these are our chemical features, so perhaps about bond length, that best separates the data based on y, or the binding energy. So you can see one question we could ask is the nickel P bond length greater than 3 angstroms? So we ask that question on the data. It splits the data into 2 buckets, one that answers no, one that answers yes. And then let's just assume that our Y value, or our chemical property we're trying to map to, ranges from -0.5 to 0.5. So this could be our binding energy. Then what will happen is, by splitting the data, what it will have done is split the data such that the Y value on the no side is clustered around perhaps a negative value, whereas this one is clustered around a positive value. And so this feature discriminates between strong and weak binding. And then we can continue to do that by asking another question, and that will split the data again. Once these buckets have very few data points, we'll stop them from growing, and we all have we assume that they'll have very tight clustered Y values. And then the one that still has data, we'll keep asking questions on it until it has very few data points left. And then at that point, we've fitted a decision tree, and we put a new piece of data in. All the questions get asked, and depending upon where it ends up, the Y value corresponding to those data points will be the Y value that we predict for that data point. Okay. But the problem with decision trees is that if they grow too large, they can overfit the data. So this can be thought of as you have a linear correlation, but you try to fit a polynomial that goes through all the points on the graph. Obviously, this will fit the data at hand very well, but if we go bring in a new piece of data, it won't fit at all. And so this is exactly what a decision tree does. It's kind of like the polynomial, and we want to turn it more into an unbiased linear model. And so to do that, we make many trees. So we build a forest, and we make a bunch of trees, each of them which takes a random subset of the data and chemical features. So the first tree gets one subset of the data, and it builds and it grows to form a particular topology. And then the second one will get different data, and so it will form a different topology. And then it keeps going on until we decide how many trees we want to build. Then once we have our random forest built, then we can provide it a new data point. So this is a set of chemical features without a binding energy, because we haven't looked at the system yet. And we can put it into the first tree. It will funnel down the tree and give us a prediction. And we do that for the other 2 trees. And we ultimately end up with 3 separate predictions, or this can be n predictions because they're n trees. We average them, and this is going to be the value that we get from the random forest. And because we've averaged together many trees, one overfitted tree can't influence the result too much. Okay, so then what we do is, using this formalism, we fit the binding energy using this a random forest algorithm. As you can see, a perfect fit would be right along this dotted black line, and we get a very good fit. And then from this model, because we're doing splitting on chemical features, we can go back in with a microscope and see what features were the most important in determining catalytic activity. And the most important features that we find are geometric features, like the average nickel-nickel bond length. So if you look at the binding energy as a function of nickel-nickel bond length, the blue dots here show our raw data. And as you can see, there's a general linear trend, or a quasi-linear trend, that as you increase the average nickel-nickel bond length, that the binding energy becomes weaker. And so you can imagine this as our nickel triangle, our nickel 3 hollow. As it's compressed, binding gets too strong. But as you essentially start expanding it, the binding gets weaker. And there can actually be a perfect point in which you achieve this thermoneutral condition. And so, based on this information, we surmise that dopants, what they're doing to the system is they're actually creating, if they're too small, they cause the system to expand, and if they're too large, they cause the system to compress. And this compression and expansion, this chemical pressure effect, is what is driving changes in the binding energy of hydrogen. And so to validate this idea of a chemical pressure effect, we didn't dope the system, and we just manually expanded and compressed the active site, and we get the orange line here. And so we can see that there's good correlation between these two, thereby helping us validate that this is an accurate model for tuning the catalytic activity of the system. And so we find that the right amount of average nickel-nickel bond length are too strong. 3.25 is far too weak. But if you're a little bit above 3 angstroms, you can actually activate hydrogen, or you can actually be active for hydrogen evolution just as much as platinum. So in summary, we understand now why nickel phosphides are almost as good as platinum. Their surfaces are enriched with phosphorus, and the nonmetal component phosphorus is an active species for hydrogen evolution. And then we discovered routes for making nickel 2P better at less reducing conditions by surface choppage and doping, and that this induces a chemical pressure effect. So in the last part of my talk, I'm going to describe a new method that we developed in the RAP group for automatically predicting surface phase diagrams. And the reason why this is really exciting for us, and specifically for the computational catalysis community, is that to date, surface reconstruction has been something that's considered only partially. And so developing a new method that can allow one to automatically predict a surface phase diagram is very useful, because then they can pick the conditions they're working at, find the surface that is stable, and then model the chemical reaction more accurately. And so the current techniques for determining a surface reconstruction or a surface phase diagram are unfortunately biased and inefficient. We obviously want an unbiased and efficient way to find them. The one way that you could do this, generate a surface phase diagram, is using ab initio thermodynamics, as developed and reinvigorated by Reuter and Scheffler. And in this method, what you do is you construct a catalog of surfaces based on your chemical intuition. So what makes sense chemically, either these can be electrostatic rules or coordination rules, and you build a catalog and you calculate their surface energies, and you can create a surface phase diagram. However, any case where you're actually curating the list is going to induce some sort of bias, and you may miss a region of the phase space of surface reconstructions that is even more stable. Another alternative is to randomly construct a large set of reconstructions, and this is work that's been refined by the group of Chris Picard. However, the phase space of possible reconstructions is really vast, and because of that, exhaustive exploration of it is really inefficient. And so we'd like to also not do it this way. A recent way of generating surface phase diagrams is using meta-heuristics, like evolutionary algorithms, which is done by the Winov group. Also particle swarm algorithms by the Wang group, and also hyperspatial optimization from the Picard group. And you can use these to predict the crystal structure. So for example, for an evolutionary algorithm, you can imagine generating a surface, and then you calculate its surface energy, and you generate a new one. And then you try to mix them together, almost like evolution. You're taking traits of one surface and traits of another surface and mashing them together, and trying to see if the new surface is even more stable. The problem is with these types of meta-heuristics is that they're unable to provide mechanistic information about the natural evolution of the surface. And so that's something we hope to add by doing grand canonical Monte Carlo. And this all begins with understanding what the grand canonical ensemble is. So you can imagine this as being a reservoir. This is our universe that we live in, and a system that's embedded within this reservoir. And the system and the reservoir are filled with particles, these round dots here. And so between the system and the reservoir, we allow there to be both heat flow and also particle flow. And so particle flow could be imagined as taking an atom from the reservoir and then sliding it over into the system. And so the probability of the system being in this particular state, with now having this atom, is going to be given by this expression, where we have a prefactor that depends on the number of atoms in the system, the volume, and also the thermal de Broglie wavelength, but also this much more familiar Boltzmann term, which the first term right here, beta, corresponds to how much heat is being transferred between the system and reservoir, but also chemical potential. And that determines how many particles are being transferred between the system and reservoir. So in order to formulate the grand canonical ensemble in a way such that we can do a simulation, we use Metropolis Monte Carlo. And specifically, we obey a condition called detailed balance. And in detailed balance, basically that states that the probability of being in an n-particle state times the probability that an attempt is made to bring a new particle in times the probability that that action is actually accepted should be equal to the reverse process, which is the probability of being in that n+1 particle state times the probability that you make an attempt to remove the particle, and then finally that removal is accepted. And so in the Metropolis scheme, we choose these to be equal. Then we can actually divide this equation in a way such that we can solve for this probability of adding or removing a particle. And so GCMC is actually able to resolve some of the problems I posed on the first slide of this section. The first being that GCMC is stochastic, and so it's able to eliminate some of the human selection bias that is present in human curation of a surface catalog. Also, it samples thermodynamically relevant structures, so it's more efficient than a random search in that thermodynamics will drive it through phase space. And then finally, in principle, it's going to globally minimize the Gibbs free energy. And so that is exactly what we want. It's going to allow us to determine stable reconstructions. So the general algorithm follows this procedure. You start by setting up a chemical potential of the atoms in the system, the volume, temperature, and also some configurational biases that prevent really unphysical structures from forming, and an initial slab geometry. Then you ask whether or not you want to add or remove an atom. If you choose to remove, then you have to pick an atom, remove it, and then you do, in our case, we do a structure relaxation with density functional theory. If you choose to add, first you have to choose an atom to add, then you choose a site in which to add that atom, and finally, we then again do a structure relaxation. At this point, we compare the free energy, or the energy of the system before the transformation and after, and we decide whether or not we want to accept. If no, we restore the previous structure and we try again. Otherwise, if yes, then we proceed with that structure and try to see how it develops. In terms of a schematic of how this might actually manifest, imagine here's again our reservoir, and this corresponds to a certain temperature, which is going to, here we choose 500 Kelvin, and also chemical potentials. And so here, the specific system that we're looking at is silver, and this is a really good model system because there's decades worth of surface studies done on it, and they have found very stable reconstructions of the surface, and we're hoping that our algorithm will be able to predict this, the most stable structure of this system. And so here we have a slab, so you can see this right here. This black line shows a slab, and the atoms here fill the slab. This bottom layer of the slab is fixed, and these atoms are allowed to relax. And so this simulates the surface because these atoms see a vacuum, and this atom is fixed, so it reproduces the effect of a stable underlying bulk material. In this region right here, we allow atoms to be exchanged, so added and removed, and we also relax the coordinates of the atoms. And so this allows us to see surface reconstructions evolve. So after n steps, you might see atoms start to fill the space, and they might form some sort of surface reconstruction. Okay. So if you run this simulation for many steps, so we ran it for 6,000 steps, you can generate a phase diagram that plots surface energy against chemical potential of oxygen. Specifically, we sample 6,000 surfaces. Each of them corresponds to a step in the simulation, and they each correspond to a gray line on the spot. We start from the silver 111 bare surface, and under different chemical potential conditions, we can see that it evolves by the evolution of this convex hull. So this green line right here shows the minimum surface free energy at that set of chemical potentials. And so we have 4 different regions, A, B, C, and D, of surfaces that we can form. Sorry about that. And just to note, in this region right here, we have a negative chemical potential. This means oxygen is very low oxygen pressure. There's not much of it around. And here it's very high oxygen pressure. So in this first regime of low oxygen pressure, we get what we'd expect. It's a bare silver 111 surface. However, as we increase the pressure of oxygen, we find that oxygen absorbs atomically on the surface. If we increase the oxygen pressure further, we don't get more atomic absorption. We actually get the formation of Ag3O4 pyramids. And this is much more stable than binding many oxygens on the surface. And also, we get these silvers. The silver and oxygen can both come from the reservoir. And so we actually form these more isolated Ag3O4 pyramids. If we increase the oxygen pressure even further to the highest pressure regime, what we find is that the Ag3O4 pyramids become distorted first. And also you can see that they start to dimerize, and that's highlighted here by these purple diamonds. And this particular arrangement of connected diamonds, this is exactly what they see, or this is very close to what they see in the literature. The only difference being that these connected diamond chains are shifted by a small amount in this vertical direction. And the reason why we don't get this exact reconstruction is because we have to use a smaller simulation cell for computational efficiency. But the key result is that we're able to see the formation of these pyramid dimers and connected chains, which is exactly what's seen in the experiment. So again, using all of this data that we generated from the Grand Canonical Monte Carlo simulations, we could then go back, calculate a number of structural features, and try to understand what are the structural features that map most effectively to stability. So what about the geometry is making the system stable? And so we looked at a number of features. Here again is a plot of how important it was in the model as a function of the feature. The 2 ones I've highlighted here are the most important ones, and they are the coordination number of silver with oxygen and the bond vector from silver to oxygen. And so the coordination number is easy to think about. You can just imagine how many oxygens are surrounding silver in its a local chemical environment, and we find that the preferred number is 2. And this makes sense because on top of the silver surface, it is known that a silver oxide forms. And the surface lattice constants of silver are very close to that of the oxide Ag2O, which exhibits this exact coordination number of oxygen. So this confirms, this confirms the validity of this being a very important feature. And actually, if you go back and look at all the reconstructions that have been studied experimentally and theoretically, most of the stable ones exhibit this feature right here, a value of 2. Also, we find that a bond vector from silver to oxygen should be small but non-zero, What I mean by that is you can imagine the coordination environment with silver pointing, with its bonds pointing towards oxygen. It would have a bond vector of 0 if the oxygens were lying along this dotted line. And that would be because the bond vector in this way would directly cancel out the bond vector in this way. However, if there is a bend or an angle between this oxygen, silver, and oxygen, then what you'd expect is a non-zero bond vector in this direction. And so we find that the bend should be about 5 degrees. And again, this is something that's seen in almost all of the surface reconstructions that are found. And so another benefit of running a grand canonical Monte Carlo simulation is that you're allowed to look, or you're able to look at the stochastic history of your system. So how is it evolving as a function of the Monte Carlo step in the simulation? And this enables us to come up with possible mechanisms for how these surface reconstructions form. And so it all starts with atomic adsorption of oxygen, and then another oxygen has to bind nearby. At that point, a surface silver vacancy forms, but that silver comes to the surface layer and forms a chain. So it all starts with forming a chain on the surface of silver O2. Then this chain elongates. So silver comes from the reservoir, and oxygen comes from gas, from the environment. Then that chain elongates further, but this time it branches. At this point, the branch chain doesn't want to have this geometry. It wants to undergo a reorganization to form a pyramid. And so this is the formation of the pyramids that we saw. Then the pyramid starts to form chains. So first the chain branches off, and it continues to grow longer. And finally, it reaches a geometry in which it also wants to relax. It's a more stable configuration. It undergoes this concerted rotation on the surface. And finally, another silver comes from the reservoir and completes our dimer. And the dimer then can form connected chains on the surface, which is, again, what we find and also we found in the experiment. So to see this a bit more dynamically, but don't mistake this for actually being dynamics, this is a stochastic history. This is a stochastic simulation. And so these events don't represent moving forward in time, but rather moving through the ensemble of surface structures. And so you can see how we might move through that space to reconstruct the surface to the most stable one. You can see here, there's a monatomic adsorption, chain formation. Then it forms the pyramid. At this point, the pyramid is going to form a branch over here that'll connect. And it'll happen rather quickly. So there, it connects, and then everything undergoes a concerted rotation. And at that point, there's just a few more lattice sites that silver needs to fill from the reservoir, and then it forms this two-dimensional connected surface reconstruction. So what's really amazing about this is that this reconstruction took almost 40 to 50 years to solve through tons of effort from both experimentalists and theorists. However, through almost only about 2 weeks of computer time, though heavy computer time, we are able to run a simulation that started from the bare silver 1-on-1 surface and automatically found its way through a complicated phase space to the most stable reconstruction. And so we really think this could be a promising tool for computational chemists, specifically those working in catalysis, in order to find surfaces that are stable and in order to do their catalytic studies. So in summary, we developed an ab initio grand canonical Monte Carlo algorithm that predicts surface phase diagrams with minimal input, generates a rich data set of structures and energies that allows us to understand what features manifest or drive stability in the system. And then we can also look at pathways for surface reconstruction on the surface, which can be then the starting point for future dynamical studies. And what's not shown is we can also extend this to nanoparticle growth, which is another avenue of research we're interested in. Okay, so from these two projects, there are some natural directions I want to go in next. The first is looking at machine learning powered computational nano-electrocatalysis, which is what I'm calling it. As I showed you before, that surface reconstruction is very important, but also particle morphology in catalysis is also very important. And so what we're interested in doing is understanding what is the wolf shape of different catalysts. So this is the shape that has the minimum total surface energy of the system, where different colors correspond to different actual cuts of the surface, and then answering the following questions. For example, how does the wolf shape depend on applied potential and pH? So we know how the surface can evolve under these conditions, and so how does the surface evolving change the predicted shape from the wolf algorithm? And then, can we relate synthetic environment to catalytic activity? And so if we're changing the stability of different surfaces and changing the morphology, how does this change the number of active sites on the surface? And so can we actually predict morphology averaged catalytic activity from first principles? Also, if we include surface reconstruction, how does this change the predicted wolf shapes? Most of the time, people consider cuts of the surface that don't include surface reconstruction to generate these figures. However, if we include them, how does that change the picture? And finally, how can we actually go about calculating the binding energy of hydrogen at these low symmetry sites, like edges and corners? These could be very important. For example, they're very important in molybdenum disulfide for hydrogen evolution. So can we find some computational way of calculating the binding energy here? And it's been shown that what you can do is if you calculate the binding energy on these different faces, you can use a machine learning algorithm that takes information about those different facets and says, what is an edge site in terms of all these different facets? Can we write the edge site binding energy as a function of these different binding energies? How do their atomic environments correlate with this atomic environment? And so in that way, you can do a regression that enables you to calculate binding energies here. And this is one thing that I'm looking at doing. But as for extending ab initio grand canonical Monte Carlo, another area of research we're very interested in is the simulation of grain boundaries. And so it's a long-standing question in the material science community as to what is the crystal structure at a grain boundary. And so we have a technique now that could be able to directly address this question. So you can imagine here, this is a slab model of STO, where you can see here that there's a dotted line. You can see how the crystal there's this diagonal in the octahedron of the titanium, and this is a twin boundary in the material. And what we could do is, at another twin boundary in the material, we could create a vacuum space. This simulating essentially the space between two grains of a material. And then this basically is analogous to a surface reconstruction problem. And then we can go ahead and use the same type of technique to develop a complexion diagram, where complexion corresponds to the structure that exists in this space. And so as for research questions, the things we would be very interested in understanding are what are the structure and composition of these complexions under different conditions, so under different temperature conditions and also chemical potentials. And then go back to understanding how do bulk properties depend upon these complexions, because if you change the structure in the bulk, that might result in bulk properties changing, and that would be very interesting. And then finally, what is the relationship between the crystal and electronic structure of the complexion and its stability relative to others? And so this is along the lines of using machine learning to understand structural and electronic properties of the system and mapping them to something like stability or a property of interest that we're interested in. Okay, so anyways, to sum it up, I just want to acknowledge a few people. I first would like to acknowledge my advisor, Professor Andrew Rapp. I truly appreciate his guidance. He's given me a lot of freedom to explore interesting problems, and it's been just a wonderful experience interacting with him. My theoretical collaborators at Penn, Dr. Mark Martirez, who mentored me in my early projects, and Mr. Tian Chu, who was a very important part in helping me to develop the Grand Canonical Monte Carlo, and is in fact a co-first author on our JPCC paper. Also my experimental collaborators at Rutgers, Professor Chuck Dismukes, who his insight was really incredible for understanding electrocatalysis, and Dr. Anders Larsen and Karen Covino for constant interaction, asking questions about how to understand experiments. Finally, I'd like to thank our funding agencies, computational support from NERSC and DoD, and last but not least, the entire RAP group for being a wonderful place to come to every day to go to work, and interacting with you all has been just really awesome for the last few years. So thank you very much, and I'd be happy to answer any questions that you have.
Okay, so at this time we can ask for questions from the general audience. Anyone, if you would like to ask something, you're welcome.
Yes.
Hi, Robert. Really nice talk.
Thank you.
So I have two questions. One, so when you were trying to find different features from density functional theory calculations, mapping those to what using machine learning to what the Gibbs free energy might be, did you comment on the importance or significance of charge density or electronic structure in general? And also for your Ni2P structures, are those for your hydrogen absorption, is that dependent on the coverage on that surface of hydrogen, or you just absorbing a single hydrogen per unit cell?
Right. So I'll start with your first question, which is about the importance of charge descriptors in mapping property to, or in mapping chemical information to a property of interest. In principle, it's very important. And so in our catalysis work where I did machine learning, which was for the doping that induce chemical pressure, we found that charge on the atoms of the dopants nearby the active site can play a small role. However, the system is overall metallic, and so changes in charge farther away from the active site are going to be screened. And so there was a minimal electronic effect there. And that's even more pronounced for the silver case, because silver itself is a metal. And so we actually were trying to find we actually didn't set out to calculate electronic features for silver. It's possible that it could be somewhat important, but I don't imagine it being very important just because of charge screening. But yes, it's an interesting question. And remind me your second question.
So in regards to like your hydrogen coverage
Yeah.
and your Ni2P, like is that significant in like your in predicting the Gibbs free energy? Like is that Gibbs free energy dependent on how many hydrogens you have on the surface? Or is that calculated based on like some equilibrium coverage?
Sure. Yeah. So yes, the binding energy in principle does depend on coverage. However, on this particular site, they bind so strongly and they're kind of spatially isolated from one another at the nickel hollow site that the binding energy is pretty much equal at each site. And I can show you that if you can. I'll do it. Here. So this isn't the nickel 2P system, this is nickel 5P4, but you can see here the nickel hollows, which are what's exposed on nickel 2P. You can see the binding energy doesn't really depend on concentration. However, these weaker binding sites, so if you have phosphorus sites available on the surface, then the concentrate or the coverage effect can be much more pronounced.
So your Ni3 hollow systems, like since you're binding so strongly, like would you proceed with absorbing more hydrogen on that system, or would you just leave it as is? If that makes sense. So like, I mean, it's like you're binding so strongly. Would you just continue to absorb more hydrogens, or would you just leave it at that coverage? Like
So what we simulate at is the saturated coverage at a particular applied potential. And so wherever hydrogen will bond spontaneously, we place it there.
Okay.
The idea of what we were trying to do is that it binds so strong, we want to try to modify the local environment to push it towards weaker binding.
Okay, understood.
Thank you. Yes?
Well, I'm interested in this machine learning to map certain features to a property of interest.
Yeah.
Could you use that to inform your choice of computational theoretical methodology? You made some comment, I'm remembering, about finding structural parameters to be the most important, like how do you or something along those lines. Well, there are certain computational techniques that will get structural parameters more accurately. There will certain techniques that will get electronic parameters more accurately, so on and so on. Would you use this machine learning then to select a computational methodology? I'm thinking here of the idea of looking to see what's important and then identifying the cheapest technique that gets that particular structural or that particular parameter accurately.
Sure. In order to do that, the first thing you would need is some sort of accurate reference, of course, against whatever type of other method that you might be employing. But in principle, if your method predicts good structures and you expect that the major effect on your property will be a structural one or a steric effect, then you could use something that provides a less robust quantum mechanical description, but a decent structural description. So something like molecular dynamics or a semi-empirical quantum mechanics. However, if you want, in terms of actually determining the method that you would need, I think that you would need some sort of reference database in order to be able to compare how close you are getting to predicting something accurately. Because when you're using these methods, it's difficult to say whether you're being quantitatively accurate about a particular property or chemical feature.
Any other questions?
Yeah.
Just a clarification is like 31, you have multiple lines in the place.
And you mentioned 6,000, is that 6,000 for each chemical potential? You do 6,000 initial guesses and then you do Monte Carlo?
No, so in the more detailed explanation is that we run the simulation under 5 different sets of chemical potentials, and then we run each of those in triplicate, and then we, after running a series of, maybe a few thousand steps counted over all of those simulations, and we take the best structures from those sets and then run them again.
And then you end up with total 6,000.
Yeah, and then, so it's 6,000 steps from, some of them are from different trajectories. But from the standpoint of doing a surface stability analysis, they're all, equal players.
Do you think that the number of surfaces then that you will find to be favorable will depend on how many initial guesses, initial steps?
Yeah, I do. Also depends on how far you are away from what you're trying to predict. So in this situation, we kind of knew what would happen, and so we were able to play around and experiment a bit more. Thanks, Judith.
So with the nickel phosphide surfaces, you're starting with published crystal structures to show the distances and the shapes of the surfaces.
Yeah.
And then adding the hydrogen. Have you found any, is there experimental work that shows how the hydrogen is bind distances, or is everything that you have currently theoretical?
So regarding the hydrogen bond distances to the surface, I don't believe that there are experiments showing specifically what those distances should be. Mostly theoretical at this point in terms of understanding how hydrogen interacts with the surface. However, in terms of surface reconstruction, there are experiments showing that the surface does form add layers of phosphorus, and also in connection to the doping work, there's studies that show that when you dope with chalcogenides, that the activity of the catalyst increases. And so some of the findings that we have are supported by experiment, but to date there doesn't seem to be an in situ method that's able to resolve these types of intermediates, though they're being actively developed. And I think for some model cases they've been shown to do some sort of in situ IR where you can see what's the stretching frequency that'll tell you something about the adsorbate from the surface. But as for like exact quantitative measures of bond distances, I don't think that's there yet.
Thank you.
Sure.
Okay. All right, well, let's thank Robert. Okay, so we thank the audience for your attendance, but now we ask you to exit by the rear doors and let the party
Choice of